Thanks a lot for the invitation to talk to you all about fast radio bursts. So I'm going to start off with a pretty broad overview of fast radio bursts because yeah, I can appreciate that there are probably not too many radio astronomers in the audience. And as the talk progresses, of course, slowly move a bit more towards some specific aspects of the work that we've been doing here in Amsterdam. And on this title slide already, you can see an image from one of our recent papers. I'll describe some of this work. One of the main themes of this talk is going to be about really pinpointing where fast radio bursts are coming from, not just the host galaxies, but the exact galactic neighborhoods that they're coming from. So fast radio bursts. I'm going to start actually by very briefly mentioning gamma ray bursts, because you probably already figured out that the acronym FRB is kind of a is inspired by the acronym GRB. So instead of gamma ray bursts, we're going to be talking about fast radio bursts. But just briefly, why are we interested in something like a gamma ray burst? And I think one of the main reasons that gamma ray bursts have been such an exciting field as well is because they're really pointing us towards sites of extreme astrophysics, where really rare, highly energetic events are happening, where we can learn something unique about all of the various weird beasts that there are in the universe, and also to some extent use these events as probes of intervening material. And that will also be an important theme of this talk. So gamma ray bursts are exceptionally bright. Can detect a couple per week at this point. And we can do so using all-sky monitors. And we're not at the point yet where we have a sufficiently sensitive all-sky radio monitor to do this type of work for FRBs. But we're getting there. And until recently, kind of the state-of-the-art FRB finder was the Parkes telescope. And the Parkes telescope discovered the phenomenon about a decade and a half ago and made many of the early discoveries. But the Parkes telescope had a field of view of less than a square degree. At the time, fairly large field of view for a radio telescope. And that meant that one could detect about one FRB every 10 days or so with Parkes. Now, because of the scientific interest in fast radio bursts, obviously there's been a huge amount of investment and work going in towards discovering and studying fast radio bursts. The current state-of-the-art FRB finder is the CHIME telescope in Canada. And that now has a field of view of about 200 square degrees, so orders of magnitude larger, and is detecting several FRBs per day, right? So we've made orders of magnitude increases in the last decade, and that's led to some pretty incredible results, some of which I'll be showing during this talk. Now, the other big difference between FRBs and GRBs is I would argue that FRBs are much more interesting probes of intervening material and magnetic field. And that's because if you look at this equation at the top here, really the observed signal that we're seeing from an FRB, the intensity as a function of time, is very much not the emitted signal, this S of t here, because that signal is modulated by all kinds of propagation effects. It's modulated by both diffractive and refractive scintillation. So the light beams are bending and interfering with each other. We see something akin to the twinkling of stars in the case of FRBs. We see scintillation. The signal is delayed towards lower frequencies because as it's passing through an ionized medium, the speed of light is frequency dependent. So we see an FRB signal actually arriving later at the lower frequencies that we're observing with the radio telescope. We need to correct for this, but this provides us a very powerful way of measuring the column density of material between us and the source, at least the ionized column density. We can see other effects as well, including, for instance, scattering, where we can actually see the effect that the rays are traveling at lower frequencies a larger distance because they've been scattered back into the line of sight. So these are all properties that we can measure with fast radio bursts. And of course, people have been doing this for decades with pulsars within our own galaxy, but now essentially we have these probes out to very large extragalactic distances, which is really incredible. So the first established fast radio burst is also termed the Lorimer burst because it was discovered by Lorimer and colleagues using the Parkes telescope. This is back in about 2007, or at least that's when the paper was published. In the meantime, the field has really exploded, as I'll be showing in this talk, and it's also entered the public consciousness as well. So if you Google fast radio burst, or for instance, if you look up fast radio bursts on Spotify, you'll find various bands whose cover artwork In this case, for instance, this is a plot that I made for an FRB paper that's now the cover of some album of some band. There's a band called Fast Radio Burst. There's a band called Lorimer Burst. It's really, percolated in the public's imagination, and I think largely because one of the overarching questions about fast radio bursts is what produces them. So this, scientific mystery really resonates with the public quite well. So here are some facts about fast radio bursts that may shock you. They may not shock you. We'll see. But I want to mention them nonetheless. One is that they last about 100 times shorter than the blink of an eye. So FRBs typically have durations of a few milliseconds or so. If you blink your eyes, that will last for about 200 milliseconds. As I'll show you in this talk, we're even finding FRBs that last a very small fraction of a millisecond. So they're very ephemeral signals. We now know that they really do come from galaxies far, far away. So they really are extragalactic signals, although we have one magnetar in our own galaxy, as I'll briefly mention, that may be an FRB emitter as well. And in that short amount of time, the burst is carrying about as much energy as the sun produces in one day. And they're really abundant. So in this artist's conception, you can see a bunch of FRBs popping off on the sky. In fact, we think that there's probably an FRB at least once every 10 seconds or so. Depends, how faint you want to go down the luminosity function. But FRBs are happening very, very abundantly. So if you had large radio eyes, it would look like a fireworks display in the sky. And in the time that I've been talking so far, there have been dozens of FRBs, maybe some of which have been detected by a radio telescope on Earth. And they're coming from very far away. So despite the fact that they last for a very short amount of time, when they were produced was a long time ago. And this is obviously not a general audience, but I'll mention this briefly anyway, because I think it's pretty mind-blowing. If you think about it, these signals are lasting for, like I said, 200 times shorter than the blink of an eye, but they're coming from hundreds of megaparsecs or even gigaparsecs away. So basically, whatever produced the event is lasting for a few milliseconds, which is hard for us to comprehend how short a millisecond is. It's not akin to our normal experience. And then that burst is traveling through extragalactic space for hundreds of millions, if not billions of years or so. And during that time, if you think about it, life developed on Earth, multicellular life developed, life crawled out of the oceans and whatnot. And then we built a radio telescope just in time to point in that direction of the sky and catch this very, very short duration burst when it arrived at that part of the Earth. So the time scales and the length scales we're dealing with here are pretty incredible. Now, as I said, one of the overarching questions about fast radio bursts is what produces them. So this is kind of a montage of some of the theories that have been postulated. In the early days, there were a number of galactic models. I think we've pretty conclusively ruled them out. We understand that FRBs come from extragalactic distances. But although there's a whole class of models that's focusing around highly magnetized neutron stars, so-called magnetars, producing fast radio bursts through the release of magnetic energy, the community has really not converged on a single model for what is producing fast radio bursts. We don't know whether they necessarily all come from magnetars, or whether maybe some of them come from accreting systems or interacting binary systems. And I would put my neck out far enough to say, I think a lot of these mechanisms are pretty plausible, and it's quite possible that within the observed population of fast radio bursts that we have so far, that multiple source types can actually be found. Because we've opened up such a large parameter space with the latest generation of radio telescopes that it wouldn't be surprising to have actually discovered multiple types of fast radio bursts at this point. So despite the fact that we might not ever conclusively know what produces fast radio bursts, or it might take a lot of work to really come to a definitive conclusion, you could ask the question, what good is this type of signal to anyone anyway? Why should we be interested from a scientific point of view beyond just the mystery of what produces them? Well, I would argue there's several reasons why this field has a very bright future. One of them is again the idea that they are sites of extreme energy density, so I think they're going to be important for probing extreme astrophysical processes. Could be pointing us towards a new type of astrophysical phenomenon. But I would say perhaps most importantly, they're really unique and very powerful probes of intervening material, ionized material and magnetized material. because every FRB that we're seeing, of course, the signal is being modulated by these propagation effects that I told you about at the beginning of the talk, and we're really probing the local environment of the FRB, the host galaxy, the interstellar medium of the host galaxy, the circumgalactic medium of that host galaxy, the intergalactic medium, potentially if there's a foreground galaxy, also the circumgalactic medium of that foreground galaxy, and of course the whole electron column density and magnetic field of our own Milky Way, the halo and the interstellar medium. And we can dissect, in some cases, these different contributions. And I told you about dispersion, this frequency-dependent light travel time. This is allowing us to measure the full column density of material along the line of sight. We can also measure how clumpy that material is, how it's distributed along the line of sight through measuring scintillation and scattering effects. So here you're seeing basically the spectrum of a fast radio burst where at certain very specific frequencies the signal is brighter or less bright. It's twinkling, that's scintillation. And we can also measure magnetic field strength. So here on the right-hand side, what you're seeing is the Faraday rotation effect, where effectively the polarized signal, it has some angle on the sky. That angle is rotating as a function of frequency due to a line of sight magnetic field. So we can measure magnetic field strengths as well. So this is the advantage of having a short duration bright radio signal. So in the case of the Lorimer burst, which was found over a decade ago, at the time of discovery, this was a really odd signal because effectively what was odd compared to a normal radio pulsar signal, just so everyone can appreciate this, was not the fact that the signal was dispersed. Normal pulsars show this effect due to the travel of the signal through the interstellar medium. What was peculiar about this is the amount of delay. So the delay in arrival time from the highest radio frequency that was measured to the lowest radio frequency. If that was purely due to the interstellar medium of our Milky Way, then we would expect a delay which is much, much smaller than what was actually measured, right? So at the time of discovery, this was noted by Dunk and his collaborators, and they ascribed this superfluous dispersive delay to the signal having to have traveled through the intergalactic medium and likely also the interstellar medium of a host galaxy. So at first, and for a very long time, this was actually the only strong evidence that these signals were coming from extragalactic space because they had this very large dispersive delay. We now know, because we've localized these sources to host galaxies in some cases, that they are definitively extragalactic. But imagine yourself at the time of discovery, you see that this dispersive delay is very large, and you infer what the distance might have been. You come up with a distance of maybe a gigaparsec or so, depending on your model for how much stuff should be in the intergalactic medium. And you realize that fast radio bursts, if you were to plot them on a diagram, phase-space diagram of duration, so on the x-axis here is essentially how long various types of radio transients last for. This is the regime where the transients last about a millisecond or so. And then we have luminosity on the y-axis. The fast radio bursts, depending on what exact distance you ascribe to them, are many orders of magnitude, roughly a factor of 1 trillion brighter than normal pulsars. Suggests that the emission mechanism has to be different than what we see from normal pulsars. So this was a fantastic discovery at the time, although it was met with a lot of skepticism, I would say. It seemed too good to be true. And a lot of people search for fast radio bursts following the discovery of Lorimer burst, and without much success in the early years. And I think people became increasingly frustrated and skeptical about the phenomenon until a PhD student at the University of Manchester in 2013, Dan Thornton, discovered a population. He discovered four sources, again using the Parkes telescope, and really definitively proved, I think, that these sources are astrophysical in nature. So I'm not going to get into the whole history of how the field developed in the early days, but I think there's a lot of very interesting sociology, astrophysical sociology going on here about how people pursue strange phenomena as well. And I think now that we know about fast radio bursts, we realize that this is probably something we could have discovered decades ago, actually. But people normally chase the things they know about instead of the things that they don't know about.
Jason, is there an easy way to understand why it took 6 years in between the discovery and the finding the small population 6 years later?
Yeah, it's it took with the Parkes telescope, it took a solid 10 days of observing, so a few hundred hours to detect a single signal, and that's a lot of observing time. Not only is it a lot of observing time, that's kind of a best case scenario. You need to back in the day, you had to do a fair amount of you needed to have a fair amount of computing power to search that parameter space. And I think there was maybe a group of a few people who were really quite dedicated to the goal of finding more of these signals. It was not trivial, right? And people were not in the early days so ready to hedge their career on doing a big observing campaign and potentially not finding anything. That was complicated also by the fact that there were various interference signals that were found at the Parkes telescope that kind of looked like FRBs a little bit, and people kind of threw up their hands and said, well, they must all be interference as well. Yeah, but nowadays we have a whole host of radio telescopes around the world that are searching for fast radio bursts. I mentioned the CHIME telescope already, but really it's one of many experiments going on worldwide. These various experiments have strengths in terms and weaknesses in terms of how well they can discover new sources and how well they can localize them. So they're complementary in many ways, and I'll be describing some of these observatories and some of the results in the rest of the talk. But before I do that, one of the things that I want to emphasize is that we now know that some FRBs can repeat. And this is, to some of you, probably somewhat old news because we've known this for about the last 5 years or so. But with the Arecibo telescope, it was discovered that there was a source of fast radio bursts that was producing repeat bursts. And we knew that it was the same source because the direction on the sky was the same, but also the amount of dispersive delay, which is essentially a proxy for distance, that was the same between bursts as well. So these are the various bursts that were found in the first set of observations. Here, that delay as a function of frequency due to dispersion has been corrected for, so the spectra are straight in time in this case. And this was quite a phenomenal discovery in the sense that it's not so often in science that you have an observation that so clearly can rule out a class of theories, right? Normally it's possible to kind of tweak your hypothesis, tweak your theory a little bit to try and accommodate new observations. But if you have a source that's producing repeat bursts, well, at the time there was a set of models that ascribed fast radio bursts to cataclysmic events. This could be, for instance, the implosion of a hypermassive neutron star. It could be the merger of compact objects. But that's not going to work for a source that's repeating, because whatever engine is producing this energy and bursts, it needs to be longer lived to be able to produce bursts over timescales of not only weeks or months, but really years at this point. And the source is still observed to be producing bursts. So we now know that there are at least kind of two broad classes of fast radio bursts. There are hundreds of bursts that have only ever been seen once, despite repeat observations. We call those one-off FRBs. But we also have a few dozen repeaters that have been observed now, which are not fantastically prolific in their bursting. It takes a lot of work to catch some bursts from them, but we know that they can produce more than one burst. And what was nice about this source at the time was there's a big practical advantage to having a repeating source, because it makes it easier to do follow-up studies. You can point all of the world's best X-ray, gamma ray, radio interferometers at this source, knowing that it's going to produce more signals, and you can see what else you can learn about this source. So a lot was learned from this first repeating source. One is that the first thing that you want to do is try and localize very precisely where the bursts are coming from. So the Arecibo telescope provides, pretty good localization, but certainly not nearly good enough to figure out which galaxy the bursts were coming from. So as kind of a toy comparison here, this is the Arecibo localization precision, and then this, just for illustrative purposes, this is a Hubble Deep Field, and you can see within that area of sky, you expect there to be lots of galaxies. You really need to localize the direction on the sky to at least arcsecond precision to definitively figure out which galaxy the bursts are coming from. And that was possible for this first repeating source. So this slide is actually summarizing many months of work from dozens of people and many papers, but effectively it was possible to localize these millisecond duration bursts, not just to arcsecond precision using the VLA, but using the European VLBI network, which is a larger radio interferometer with higher spatial resolution, it was even possible to localize the source to milli-arcsecond resolution, and thereby identify the host galaxy, determine its spectrum and hence redshift, characterize a galaxy, which turned out to be quite a low mass and low metallicity, high specific star formation rate dwarf galaxy. And what was interesting about this source is, it was in this low metallicity environment, high specific star formation rate. There was a knot of star formation that was found at the location of the source. There was also a persistent source of radio emission that was found that could be perhaps some kind of nebula around the source. This was, for a while, this was kind of the prototype of what these repeaters would look like, but it was a prototype only in the sense that we'd only found one, and the ones that we found after that don't really fit the model as well. No X-rays were found at the location, so this is an ongoing frustration in FRB science. We haven't been able to find any multi-wavelength counterparts to the bursts yet, either optical or X-ray or gamma ray. But we had a pretty complete characterization of this source and its environment. We took it even further by, for instance, looking at the polarimetric properties of the burst. And it turns out that a lot of fast radio bursts are almost 100% polarized. So whatever is producing the burst it's imparting a very preferred direction. You could imagine, for instance, that the bursts are being generated in in an environment with a strong magnetic field with a preferred direction, and that the emission region has a preferred direction, and hence the bursts have a high linear polarization fraction. What this graph is showing you actually is that the so-called Faraday rotation measure, which measures how much that polarization angle is rotating due to the line of sight magnetic field, the amount of rotations across the observing band that we are able to record is very large. There are 50 rotations across this observing band. That gives you something that's called the rotation measure, which in this case was about as high a rotation measure as you would basically only see towards a galactic center-like environment. So for instance, if you look towards Sagittarius star in our own galaxy, there's a magnetar close to Sagittarius star. You can measure its rotation measure and hence probe the magnetic field strength in the vicinity of Sagittarius star. You can do this for active galactic nuclei as well. And the Faraday rotation measure that we measured for this first repeating fast radio burst source was comparable to those types of environments, suggesting that it's maybe in some kind of galactic center environment, maybe around a massive black hole, or alternatively, and Tony has worked on this, maybe it's in some kind of dense supernova remnant or nebula. That's also possible. We don't know yet. We've also seen that because we are able to study the source over and over again, that the emission properties are also very characteristic. So again, these images of bursts that I'm showing you here, they're showing you the radio frequency versus time. And there are a few things that you can note here. First is that I've already corrected for this delay, this dispersive delay due to the intervening material. And despite having corrected for that already, you can still see that the burst is not arriving at the same time at the same frequency. It seems to be drifting downwards. And also the spectrum is not broadband either. It peaks in radio frequency, and that peak radio frequency is drifting to lower frequencies while the burst is happening. This is called, we call this in the field, colloquially, we call this the sad trombone effect, because it's kind of like someone tells a bad joke and then someone plays a sad trombone in the background. This is something that is, I would say, not unprecedented in radio bursts in general, because if you look at certain types of radio bursts from the sun, you also see this kind of drifting pattern. And we think this has to do with the emission region propagating towards higher altitudes where the plasma density and magnetic field strength is lower, at least in the case of the sun. So something similar to that might actually be happening around the sources of fast radio bursts as well, that we can actually see dynamically how the emission region is changing as a function of time. And on the left-hand side, if you're curious what's being shown there, this is a 3D print of what the burst looks like as a function of frequency, time, and brightness. Now, fortunately, some very clever people have created experiments that can now localize non-repeating sources as well. So we're not stuck with only being able to figure out the host galaxies of repeating sources. This includes the ASCAP telescope in Australia. which can both discover and localize sources because it has a large field of view, and also because it's a distributed interferometer. It can have, scan a large area of sky and also pinpoint directions very precisely, as well as not too far from where you all are, a few hundred kilometers away, I think, in Owens Valley, there's the deep synoptic array, which is now being upgraded actually to 110 dishes by Vikram Ravi and Greg Hellenan et al. So now we're in the luxurious position that we have hundreds of FRBs that have been discovered, dozens of repeaters, also roughly speaking about a dozen or so sources that have been precisely localized. And this is great because we can start, studying in detail the host galaxies of fast radio bursts, but it hasn't provided really all that much clarity at this point, because we seem to be finding FRBs in a whole host of host galaxies, if you will. So the first repeater was found in this dwarf galaxy, and people, including myself, at first said, aha, this is a very characteristic environment. This must be telling us something. But of course, the next source was found in much more massive galaxy with a much higher metallicity. So it didn't really fit the picture. And then sources since then have been found in other environments. And as I'll show you, we've even found one of these sources in a globular cluster. So the picture has not really crystallized in a way that has provided clarity all that quickly. And one of the case examples that I want to show you is this quite nearby repeating source, the second well-localized repeating source, which I'll explain a little bit what we've learned from the second example of a well-localized fast radio burst that's repeating. So this source was found by the CHIME FRB experiment, which again is this fantastic FRB finding machine in Canada. It's scanning 0.5% of the sky at any given time, which for a radio telescope is really impressive. They've now discovered over 20 repeaters, and one of the repeaters that they discovered appeared to be quite nearby. And again, CHIME has this huge field of view, which allows it to find lots of fast radio bursts, but its localization precision is currently limited due to the fact that it's not an interferometer. It's being upgraded to be an interferometer in the future, but the localization on the sky is pretty limited with the current system. So what we did is we followed up with the European VLBI Network, which is this global network of radio telescopes whose signals can actually stream in real time to this little village in the Netherlands called Dwingelo. So you have hundreds and hundreds of gigabytes per second that are streaming into this little village in Dwingelo, where about 2,000 people live, and a large fraction of them are astronomers. And this is for comparison, the full moon, this is kind of the localization that CHIME was able to achieve by discovering the source. And this is the field of sky around that area. This is taken with Gemini, and you can see there are a bunch of stars, obviously, and there's some galaxies in the field, some of them fairly bright, some of them faint. It's only possible to figure out where the burst is coming from by localizing it interferometrically. So we did that with the EVN by catching more bursts, and we were able to improve the localization of the source by a factor of a few billion in terms of the area of sky that it was constrained to. And this allowed us to figure out the host galaxy. So this is a host galaxy, it's a relatively face-on spiral galaxy, and specifically not just the host galaxy, but also the area of the host galaxy, the neighborhood from which the bursts are coming. So the bursts were coming from here. It seems in retrospect a little bit obvious because there's an arrow pointing right towards where the burst is coming from, so we should have known. We also, in the meantime, in parallel, as we were finding the host galaxy, CHIME was able to figure out that the burst activity is actually periodic from this source as well. So what these various graphs on the right-hand side are showing is essentially, if you look at how active the source is in terms of how often it's producing bursts, you'll realize that the source becomes active every 16.4 days or so. So there's some cycle, could be an orbit, could be rotation, could be precession, we don't know, but there's some cycle that is causing the source to become more active and less active. So keep that in mind. Follow-up observations with the Hubble Space Telescope were really aimed at making full use of the very high precision localization that's possible with a very long baseline interferometer like the EVN, because you can localize the position of the burst to a few milli-arcseconds, and Hubble has a spatial resolution of maybe 60 or 70 milli-arcseconds or so. So you can really study in the finest possible detail the local environment. And what we found was that V-shaped region of the galaxy actually breaks up into a few knots of star formation. And interestingly, we see that the position of this source, which is also colloquially sometimes referred to as R3 because it was the third repeater ever to be discovered, is not really on top of the peak of star formation. It's offset by, well, at the distance of the host galaxy, which is about 150 megaparsecs, it's offset about by 200 parsecs or so. So this is interesting. We might have expected that the source would be right on top of the most active area of star formation, because you might prefer to have a model where you say, well, fast radio burst engines must be maybe very young neutron stars, very, very young magnetars. So you'd expect them to be where such sources are being formed. If you were to assume that the source has to be formed in that star-forming region, and it wasn't formed in situ, then of course you can play the game of considering the offset and the transverse velocity and try and constrain an age. So if you assume that the source was born in that star-forming region, given the typical velocities of neutron stars, it would have taken at least hundreds of thousands of years for it to move to its current location. So maybe it's not such a young source. And the last thing that I'll say about this source is it has so far provided us with one other, well, actually two more really interesting insights. One is, again, I tried to emphasize this kind of range of timescales that we're starting to probe with fast radio bursts. These sources are being discovered in surveys where we're typically observing at kind of millisecond timescales to find these bursts. But if we can, after the fact, zoom in time down to microsecond or nanosecond timescales, there's a lot to be found still. So this was work that was done by one of my PhD students here in Amsterdam, Kenzie Nimmo. She's looked at a number of the bursts from this repeating source, and what she's been able to ascertain, I'll just skip to the next slide, is effectively, as you keep zooming in on these bursts, you can find structures in the brightness of the bursts, variations on microsecond timescales, effectively. So on the right-hand side here, these peaks that one is seeing, these are only a few microseconds wide. And if you assume that, well, if you partially ignore special relativistic effects, you can use this to constrain the size of the emitting region, right? So you can use light travel time arguments to say, well, if the signal lasts for this long, then it must have been produced in a region of maximally this size. And 3 microseconds corresponds to only about 10 kilometers or so. So this is suggesting that, you know, the emission sites of fast radio bursts can be really, really constrained, spatially constrained, right? And I'll come back to this when I talk about one other source a little bit later on. The last thing I'm going to say about this source is the fact that, again, with the repeating source, you can keep observing over and over and over again with every telescope you can get your hands on, and try and come to new insights about what type of source it might be. This includes also probing the properties of fast radio bursts at the lowest possible radio frequencies that we can observe from Earth. So here in the Netherlands, we have a telescope called LOFAR, which is a distributed interferometer of dipole antennas that observes really the lowest radio frequencies, or the longest radio wavelengths that one can see from Earth, below which actually radio waves from space are just reflected off the Earth's ionosphere. And intensively observing the source, we're able to see that it is also visible down to these very low frequencies. In fact, down to a radio frequency of about 110 megahertz or so, corresponds to a radio wavelength of 2.5 meters or so longer than the span of my arms. So these really long wavelengths, factor of 10 lower frequencies than we typically observe fast radio bursts. And why does this matter? Well, one of the reasons it matters is the fact that we can even see these bursts down to such low frequencies constrains the local environment. It tells us that the bursts are able to escape from the central engine, so they aren't absorbed. There's not significant free absorption precluding the detectability of the burst. So that puts some nice constraints on the local environment. We're also able to see, and I would just focus on the top graph here, that if one compares, for instance, when the activity of the source peaks at the higher frequencies observed by CHIME, so this is radio frequency here, and this is effectively time on the x-axis, one can see that the bursts at lower frequencies, the activity of the source increases at later times at lower frequencies. So there's some kind of stable geometry in this system such that when emission is happening at high radio frequencies, that's happening earlier than at lower radio frequencies. And we don't yet know whether this has to do with some kind of large processing beam or some rotating swept back emission region. We don't know yet, but it is telling us something about the emission region. And coupled with the fact that the source is periodically active, surely must be telling us something about what actually produces fast radio bursts that repeat. And we can take this even farther. We can probe things like variations in the rotation measure and whatnot that actually suggests that the environment isn't, completely pristine, that there's some gunk around the source, some plasma that's magnetized around the source. And one of the hypotheses that we've tried to explore to explain all of this is maybe this fast radio burst source is some kind of extreme neutron star in something like a high mass X-ray binary system, where we can understand, that we're seeing the source from different angles with the 16-day periodicity, because a lot of high mass X-ray binary systems have orbital periods of a few days or so, and maybe we can understand some of these subtle propagation effects and changes in these propagation effects by perhaps the source passing through some kind of decretion disk around the massive stellar companion. Yeah, and I think there's a lot to be done in this area, because we've detected at least one other repeating fast radio burst with LOFAR as well. So I think studying the low frequency properties of fast radio bursts is really going to be an interesting area. So I want to try and conclude in the next 5 or 10 minutes or so, but I can't help about talking about this source as well. So CHIME really has been a treasure chest of information about fast radio bursts, because CHIME has been discovering such large numbers of fast radio bursts that it's also discovering sources that are relatively nearby. And that includes the recent discovery that CHIME made of a source that's in the direction of the famous M81 galaxy, suggesting that the fast radio burst may be a member of that galaxy. So this was work that was published earlier this year by Mohit Bhardwaj, who works at McGill University in Canada. You can see the M81 galaxy here. Since I work in the Netherlands, here's a picture of Oort standing next to the same galaxy taken at the Leiden Observatory back in the 1960s or so. Little does he know that there's an FRB source behind him. And what Mohit did is, so this was a localization here in the red ellipse that was determined by CHIME. So that was kind of the localization precision that they were able to get. And there were a number of sources within the field, an X-ray source, a radio source, a globular cluster in this direction. And it wasn't clear which one of those sources, if any, had anything to do with the FRB, right? And it was also kind of unclear whether the FRB was necessarily associated with M81, because it's possible that maybe it's in the background, or maybe it's a galactic halo source. Wasn't clear. So again, we did this trick of following up the source with the European VLBI array, and we are able to localize the source very precisely again. So if anyone in the audience is an aficionado with the radio interferometric imaging, here on the left-hand side, this is a so-called dirty image. So this is just the direct, Fourier transform, similar to the Fourier transform of the so-called visibilities. And then if you deconvolve that to get rid of the instrumental response, this is what the so-called clean image of these combined bursts looks like. And so this is the location of the source now determined to milli-arcsecond precision. And then you want to know, okay, what is in that direction of the sky? And you could be unlucky. There could be, nothing in the direction of the sky. And well, we haven't really learned whether it's associated with M81 or not. But lo and behold, and to our great surprise, right on top of the position of the source is a globular cluster that has been known since the 1990s to be a member of the M81 galactic globular cluster system. So this was a huge surprise, because I would not have guessed a priori that we would be finding fast radio bursts in globular clusters, specifically because globular clusters are famous as being very dense, old stellar populations. They're not the place you find young magnetars formed through core collapse, right? There's no massive stars undergoing supernovae in globular clusters. The source is pretty close to the core of the globular cluster. That's the other nice thing about having this such a high precision radio localization is that you can measure not just the fact that it's associated with the globular cluster, you can actually compare it to the half light radius of the globular cluster, and it's relatively close to the core, but it's definitely not associated with exactly the core of the cluster. So in the context of say a magnetar model for an FRB, if FRBs are coming from magnetars, then in this case, that magnetar could not have been formed through core collapse. It must have been formed through accretion-induced collapsed or binary merger. Or you could also entertain the idea that maybe it has nothing to do with magnetars. Maybe it's some kind of accreting neutron star or black hole where the FRBs are being produced in the jet of this accreting compact object or black hole. So this is really, really intriguing. And I know that people at Carnegie are also trying to understand what the most likely outcomes are. And the other thing I'll mention about this source is beyond the fact that it's exceptional for being associated with the globular cluster, it's also an FRB that tends to produce radio bursts that are very short in duration compared to your typical FRB. So on the left-hand side here, these are 3 of the bursts produced by this source. And now the time resolution that's being plotted here is at microsecond resolution. So this is 1,000 times higher time resolution than we normally search for FRBs. And you can see in the case of this one burst that even at 1 microsecond time resolution, you can still see that there are very sharp structures in this burst. And in fact, if you zoom in to 30 nanosecond time resolution, you can still see that there are structures in this burst. So we're really probing now at megaparsec distances, emission regions that have to be at most a kilometer or so. So this is pretty fun. And I think to a certain degree that these very short timescales, in my mind, they're problematic for models that involve some kind of shock for producing the burst. In my mind, they're more consistent with a model in which you have some very strong magnetospheric, you have a very strong magnetosphere around, for instance, a neutron star, and the FRBs are produced in that magnetosphere. So I'm starting to run low on time. I'll just briefly mention that another important piece of the overall FRB puzzle is the fact that we've seen an FRB-like burst from a galactic magnetar. I'm sure a lot of people have heard about this. This was detected again by the CHIME FRB experiment and the STARE-2 experiment, which was led out of Caltech by Chris Boenek. Really suggests that a large fraction of FRBs, or a significant fraction of FRBs, are coming from magnetars. One of the things that I think is really quite incredible about this as well, though, is not just this very bright burst. We followed up this burst also using some small telescopes here in Europe. We were able to detect a few more bright bursts from the source after the mega bright event that was detected by CHIME and STARE-2. And what I find particularly interesting about this source is these other bursts that were detected. They really span this whole range of luminosities from radio pulsars up to these extragalactic FRBs. We have like a single source in our own galaxy that can produce radio bursts over 7 or 8 orders of magnitude in luminosity. It really suggests to me that we've actually underestimated what neutron stars can do. And maybe that's an important part of the FRB puzzle, is that we've been a little bit too pessimistic about what a neutron star can actually do. So I think it would be good to start wrapping up the talk for real now. Maybe one of the last points I'll make before going to my conclusion slide is one that brings me back to this transient phase space diagram, because earlier I was talking to Anna about how much of a phase space, discovery space there still is for fast radio bursts, and I think this diagram illustrates that quite nicely. So again, we have the duration of events here on the x-axis from nanoseconds up to say 10 seconds or so, and then we have luminosity here. We have this well-known population of pulsars that have typical timescales of a millisecond and some characteristic spectral luminosity. These have been known for decades. We have this galactic magnetar source, which, as I just told you, spans 7 orders of magnitude in luminosity, with a characteristic timescale of about a millisecond or so. We have these extragalactic fast radio bursts that are much more luminous still, but what we've been realizing recently is that a lot of these sources also produce bursts of much shorter duration, orders and orders of magnitude shorter duration, thousands, even 1 million times shorter duration. And the point that I'm getting at in all of this is the Lorimer burst was this fantastic gift because it spurned a huge amount of activity to increase the field of view of radio telescopes to further explore this parameter space. And in doing so, I think we've realized that we're still, really in the first stages of fully exploring this parameter space, in the sense that as we become more technologically available to do so, I think we're going to be finding fast radio bursts on much shorter timescales, even higher or lower luminosities. And I think they're probably going to be associated with a whole host of different source types. So I'll go to my conclusion slides now. I'll skip over some of these other side remarks. So why do I think that this field has an interesting future? Well, again, fast radio bursts have an enormous event rate. We're seeing a fast radio burst. We can imply that there's a fast radio burst, or extrapolate that there's a fast radio burst happening every 10 seconds or so somewhere on the sky. They really provide an exceptional probe of the intervening ionized material. And that's by looking at all of these propagation effects that impart signatures on the spectrum and on the polarimetry of the burst. And also because we can localize these sources very precisely. We can figure out exact galactic neighborhoods that they're coming from. We can associate them, at least in the near universe, with things like globular clusters. I can imagine in the future with telescopes like ELT or with the 30-meter telescope, it will eventually be possible to even, for instance, identify optical companions that might be the companion star of an FRB source. And I'm sure there'll be interesting applications for that as well. So I think I'll end here. Thank you very much for your attention, and I'm very happy to answer whatever questions you may have.
Great. Thank you for the nice summary, Jason. That was fantastic. Does anyone have any questions? You could raise your hand or just speak up. I guess one question I have just to get things started is, we talk about using FRBs as probes of like the intergalactic medium and so forth. But every time you see a FRB, you're really getting an integrated quantity out of it. And so, how do we disentangle that when there's effects local to the FRB, when there's effects of, the circumgalactic medium of galaxies, intergalactic medium? There's all these different components. How do we, what's the future of that?
Yeah, for sure. That's a very good question. I think there are two approaches. One is, purely statistical, and I think it's possible to do, to beat down that kind of noise, if you want to call it noise, by having hundreds of sources to work with. So there have been a number of interesting papers that have already been written on the CHIME FRB sample, where you can cross-correlate with galaxies and show, for instance, that that there's some subset of FRBs that appear to have large local contributions. Otherwise, they wouldn't be where we see them. The other way of doing this is not statistical, but rather if you localize sources to very specific galactic neighborhoods, if you can measure, their rotation measure, their scattering properties, their dispersion measure, and if you have catalogs of intervening galaxies, you can disentangle these things because you have constraints on how strong the contributions are from the local environment. You have information about whether they're in intervening halos or not, yeah, and I think if you consider the number of properties that you can measure from a fast radio burst, there are dozens of things that you can measure, and if you couple that with ancillary information, then I think for individual sources you can also get to interesting constraints, despite the fact that there is a as you say, a mix of contributions along the line of sight. And that, maybe the last thing I'll say about this as well is, for sources that are very nearby, the constraints very quickly become very strong for things like probing the contribution of the galactic halo, like the source in M81. We know that there's not a strong local contribution because globular clusters do not have dense, interstellar media. We know that there's not a large contribution from the intergalactic medium because the source is not very far away. So the constraints on the Milky Way's halo contribution become pretty strong and not model dependent very quickly, actually.
Allison, go ahead.
Hi, Jason. Thanks for such a great talk. I had a question about probing the IGM also. Could you talk about how FRBs could be used to investigate the missing baryons that are supposedly in the IGM and how feasible that would be?
Yeah. Yeah, that's a great question as well. And there is, I didn't have time to talk about everything that's happened in the last few years, but maybe it was one of the most exciting things that I could have mentioned but didn't was a paper last year by J.P. McCart, who unfortunately passed away last year as well. He was also a very good colleague and friend of mine as well. But he wrote a beautiful paper last year in which, using a sample of half a dozen very well localized sources from ASCAP, where they're able to determine the host galaxy and hence the redshift, they were able to show the correlation between redshift and the dispersion measure, the amount of dispersive delay towards these bursts. And this is now called the McCart relationship in memory of JP. And it was already apparent from a sample of only half a dozen FRBs or so. I think once we can do this for a few hundred, if not 1,000 FRBs, then we'll be already seeing things like cosmic variance, intervening halos, and all of this. But effectively, we've detected these missing baryons already, and I think we're on the verge of being able to map them and study them much more precisely pretty soon.
If you let me share my screen, I can just show the plot real fast.
Yeah, that would be great.
Such...
It's a beautiful result. Yeah.
I mean, it was sad, but also just beautiful that he was able to get this out before he passed away. I mean, given he was such a proponent of using FRBs in this way. So this is the plot, I think, right?
Yeah, that's the plot. Yeah. And what you can see here, I mean, one of the important points is you can see that there are some FRBs that have been excluded. And that's because we know in the case of repeaters that some of them seem to be in very dense local environments. So those have less promise for probing intergalactic media because they're more influenced by the local environment. But those colored points there, those are essentially showing you that the expected relationship between the amount of intergalactic dispersion measure per unit redshift that agrees with the observations. And this is a pretty sparse sample to start with, but eventually we're going to be localizing several FRBs every single day, so this plot is going to fill in very quickly.
Any last questions? All right, well, I guess everyone's done. So thank you again, Jason. That was really fun. And yeah, thanks for visiting virtually.
Thank you.
Thanks very much. It's great.
All right.